I invite our chairperson, Dr. T. Ratnesh Das, Professor, the Department of Chemistry in Dr. Hari Singh Gaur University at Madhya Pradesh.
Hello.
Yes, sir.
Am I audible?
Yes, sir. Audible. Yes, sir. Audible.
Good morning. Good morning to each and everyone present today.
Yes,
So, our next speaker is Dr. S.N. Jha, and he is from RRCAT Indore. And today he will be talking on local structure investigation of material using EXAFS facility at Indus 2 Synchrotron Radiation Source, and he is from RRCAT Indore. So Dr. Jha has done his MSc in Physical Chemistry from Delhi University. He joined BARC in 1988, and after MSc and later in 2001, he shifted to RRCAT. He has done his PhD in X-ray spectroscopy from Mumbai University, and his research area are synchrotron-based beamline development and material science, studies using photoelectron spectroscopy and X-ray absorption technique. Dr. Jha has a huge citation that is about 6,000. His H index is 37 and I-10 index is 142. In 2022, he has published 619. He has published 58 papers. So, with this brief introduction of Dr. Jha, now I request Dr. Jha to please deliver his talk.
Thank you, Professor. Am I audible?
Yes, your voice is there.
This sustainable chemistry and renewable energy, and it is very important topic as per our national needs. So I thanks the organizer for choosing such a important theme for this conference, and I also thank the this national virtual this Universal Intellectual Trust, who is doing this wonderful job for propagating the science and for our national requirement. And I especially thank Dr. K. Rajkumar for inviting me here. And also I thank the chairman who also helped me in the morning in solving this internet issue. I was not able to connect to your site since yesterday. So with this, I also thank the chairman of the session for a nice introduction and kind introduction. And with this, I will now start my talk. And so this is the topic, local structure investigations of materials using extended X-ray absorption fine structure facility at Indus Synchrotron Radiation Source, RRCAT Indore. And the background photograph, what you see is the view graph of the two sources, the only sources of India. That is, this is the Indus 1 entrance, and this is the Indus 2 entrance. And more we'll hear in the next slides. So this is the plan of the talk. So I'll first introduce you the wonderful source, that is synchrotron source, and then I will also give glimpse of the Indian source, that is Indus Synchrotron Radiation Source, and then I will come to the main topic, that is introduction to X-ray absorption fine structure technique with slight brief history, then origin of EXAFS, then experimental methods, and also I'll stress upon the GENS part of the EXAFS technique, and then I'll also introduce with the beamline EXAFS beamline facility at Indus 2, and then I'll give some examples which will make you feel that yes, what all can be done within this wonderful technique, and then I will summarize the whole presentation. Okay, so what is synchrotron radiation? Synchrotron radiation is a source of broad spectrum of electromagnetic radiation extending from infrared to all the way up to X-ray wavelength. So at one go, we get a full continuum for using for probing the material. And also it offers unique properties which is not attainable from the laboratory sources, and it is available through dedicated national user facilities. So you can say that is one drawback, that is not that so simple like any lab source and so it involves a huge capital cost, and so it is available like a mega facility like Indus in Electra, Springate, and so on. So basically, SR is emitted when a charge or normally the electron, which is moving at a relativistic speed, and then it follows, if it follows a curved trajectory by a suitable bending magnet, and so that radiation is called synchrotron radiation. So this is very old, understood theory about the electromagnetic radiation, that any charged particle, when it is accelerated or decelerated, then it emits a radiation, and especially when this speed of the charged particle is much less than c, then its radiation nature is isotropic, as you can see here. But the moment we increase the velocity of this charged particle almost to equal to c, less than c, and then you see whole isotropic radiation, it peaks in a forward cone, like in the scooter you see the light coming like searchlight. So this relativistic phenomena gives unique properties of this wonderful source. So basically, how it is generated? It is generated and by first of all, starting with the electron source, like a filament, from the filament, and then it is accelerated in a linear accelerator, and then further accelerated to the required energy in a booster, and then injected in the storage ring, where the experimentalists use this photon source. And there are 5 major components in any SR technology. And so starting from source of electrons, like it can be electron gun, linear accelerator, or microtron, and then a booster ring. For example, here, this is the booster ring, and then a storage ring. This is the one of the storage ring, Indus 1, and this Indus 2. And then we have a radio frequency supply to boost the energy in the storage ring. And then ultimately we need device that is called beamlines to tap the useful photons for our studies. And these are some view graphs of the different components used in SR. So this is the bending magnet that I told you, using this bending magnet. So this is North Pole and South Pole, and this electron is passing through this, and then there is a bending. And these are some sophisticated other kind of magnet which uses like quadrupole and sextupole magnet, which uses to focus the electron beam in a circular path. And this is the section where the bending magnet, and this is the RF cavity used for the acceleration of the charged particle. So what is the beamline? I have used this word beamline. So basically beamline is nothing but a interface between the synchrotron source and between the experimental station where one does the experiment. And then you see synchrotron source is isolated from the user area by a thick shielding wall. So this is the concrete 3-meter shielding wall, and below this high radiation zone is there, so cannot enter in this area. So in between the shielding wall and source, we have a front end, which is a device to protect the source as well as the man using this facility. And beyond the shielding wall, which is the area where users are allowed to work upon, this consists of a beam transport channel, which has a combination of mirrors, monometers, slits, etc. And then the experimental station, where normally used in laboratory source also, like goniometer or detector, data acquisition system, all those things. So basically, this beamline is used to transport the beam with a desired quality and the quantity. Quality means the desired resolution, and quantity means how much flux, and then what is the source size, resolution. All these things is decided by this appropriate design of this beamline. So that the users get the optimum beam quality for the required experiment. Okay, so this is the glimpse of Indus 2 machine, where you can see these are the beam lines. Like this is a beam line for structural characterization, and this is the beam line for microfabrication. This is the beam line for imaging objects. So you can see this whole beam line is housed in a lead house. So this is the enclosure made out of the lead sheets, so that there is no radiation coming out of in this area for normal users, researchers. So after giving the introduction of how it is produced, and now this I have summarized here the unique properties of synchronization, and there are some of the terminology you will hear if you interact with any scientific community who is using this facility. So we call it has a broad spectrum. So basically, which means that it covers from microwave to hard X-rays. So the user can select any wavelength required for the experiment. So we have a atomic sensitivity. That's how this the topic of today, that is EXAFS, has been rediscovered by this because of the synchrotron radiation. Okay, so then it has high flux. That means what is high intensity photon beam? It allows rapid experiments or use of weakly scattering crystals. So earlier with the laboratory source, which we are very unthinkable to do the experiment, now it is possible because of synchrotron, and this EXAFS is one of the examples which has been possible because of high flux of the synchrotron, and it is defined by photons per second per bandwidth. So bandwidth means the whole continuum. If you choose a small area, small from this, so this is called bandwidth. And then it has a high brilliance. That means spectral brightness is very high. So that means a highly collimated photon beam is generated by a small divergence from the source in a small with a small size of the source. So it has very high spectral resolution, and so it is defined by photons per second per unit area per unit solid angle per unit bandwidth. And another important quality is that it has high stability, because the whole thing is in the submicron source stability, the whole arrangement. So it can be used for nano imaging. Then it has also a natural polarization. That means the beam, photon beam, which is coming out of the source, it has linear polarization in the plane of the electron orbit, and it is circular polarized in the above and below the plane of the orbit. So therefore, the signal to noise ratio for many experiments, for example, X-ray, magnetic circular diagram, or another Compton scattering, this signal to noise ratio enhances. So you can go down to very dilute samples. Then it has a pulse time structure. The pulse length down to tens of picosecond allows the resolution of processes, time resolved processes on the same time scale. So dynamic studies during any reaction can be performed. And also another important quality, you can say, it is produced in a clean environment, so there is no contaminant spectra. Since the whole electron is being accelerated and it is circulating in a ultra high vacuum chamber, which is maintained at 10 to power minus 10 millibar. So there is no any impurity element which it can interact and give rise to impurity lines, like in copper K alpha XRD, when you are getting copper K beta also. So this is another important also property. And over the years, the synchrotron source also has made different advancements. So apart from this bending magnet source, which I introduced to you initially, that just using a north and south pole combination, we can have a bending magnet source. But later on, the people have realized that just by introducing a array of bending magnets in a straight section, we can enhance the brightness or the flux of the synchrotron source further, more than 2-3 order of magnitude. And these different devices are known as wigglers, undulators, etc. I will not go into detail, but just for handshake information, I am just giving you a glimpse. And see, so over the years, you can see since from 1890, where we have sealed tubes in the day of Röntgen, when X-ray was discovered. So up to 1950, almost the flux level, the brilliance level is almost linear or constant, you can say. And then almost from 1960 onwards, when rotating anode came, there is a slight enhancement in the brilliance. And then when the first bending magnet source was fabricated, there was a 4 order of magnitude enhancement in the brilliance of the source. So whatever you see the seal tube in the hospital, see there is a 4 order of magnitude enhancement. And now in this present scenario, we have got up to 4th generation synchrotron source, which can go up to 10 power 27, 28 kind of brilliance. And this is the comparison of the different source. So this is a normal bending magnet source using just one pair of north and south pole magnet. And once you go to another advanced source like undulator and irregular, so there is a jump in the brilliance. So this advancement, the synchronization has been also categorized in 4 generations. And first generation was actually it was not meant for a dedicated use of synchrotron source, but it was a parasitic facilities, as the synchrotrons were primarily designed for high energy or nuclear physics experiments. But the second generation, after the dedicated synchrotron radiation started being used with the binding magnet source only, and so it was called second generation. So in India, the Indus 1 machine is a second generation source, but Indus 2 is a third generation source. So what is third generation? It is a source along with the insertion devices that I showed you, undulator and irregular, so which produces 3 to 7 times higher brilliance than the second generation source. And now it has come up fourth generation source also, which normally has more than 6 GeV energy of the electrons, which is circulating the vacuum tube, and with free electron laser, with a peak brilliance up to 3 to 10 times higher than the third generation source. And more than 50 light sources are available all over the different places all over the world. And this is the India, where we have the only Indus source right now available. But now there is a planning also from that we will have a fourth generation source that in the country. And this is the pie chart showing the utilization of the source. You can see the major chunk is taken away by bio life science, where the drug design, protein crystal generation, all these things are used by this source. And then of course we have a chemistry, physics, environmental science, and then industrial, all the things are there. So I'll just show you one small video clips to highlight the synchrotron source with respect.
The world around us is made up of matter, which is composed of atoms that cannot be seen by the human eye. To see atoms, X-rays, which have much smaller wavelengths than visible light, are needed. Other invisible radiations like ultraviolet and infrared rays are useful for studying vibrations of atoms in molecules. Laboratory-based experiments to probe atomic scale phenomena are often limited by lack of sufficiently bright and tunable sources of these radiations. The synchrotron radiation source, which is one of the marvels of modern science, produces highly intense radiation spanning the entire range of visible as well as invisible wavelengths. What is synchrotron radiation? When any charged particle, like an electron, is accelerated along a circular path by the action of a magnetic field, it emits what is known as dipole radiation. When the speed is increased till it is close to the speed of light, an extremely bright and well-directed radiation is emitted. The machines used to accelerate electrons to such high speeds are called synchrotrons, and the emitted light, which contains all wavelengths from infrared to X-rays, is called synchrotron radiation. In a synchrotron radiation facility, electrons emitted by an electron gun are first accelerated in a microtron or linear accelerator, after which they enter a circular accelerator called a booster synchrotron. Here, the energy of the electron is boosted up to high speeds, approaching the speed of light. Next, the electrons are injected into a storage ring made up of alternate straight sections and curved sections consisting of different types of magnet arrangements. In the storage ring, they circulate at a constant speed for several hours or even days. The emitted radiation is used for different types of experiments. Over 50 light sources are in operation all over the world, including the Indian synchrotron radiation sources Indus 1 and Indus 2 at the Raja Ramanna Center for Advanced Technology at Indore. Scientists from physics group of Bhabha Atomic Research Center have set up several experimental facilities at Indus 1 and Indus 2. The fundamental parameters used to probe the physical world have given rise to various experimental techniques. For example, in photoelectron spectroscopy, X-ray photons knock out electrons from the sample. By measuring the energies of these electrons, valuable information is obtained about the energy levels of the atoms in the sample. In X-ray diffraction, incident X-rays are scattered from the sample and interfere with one another to form a diffraction pattern. By analyzing this pattern, scientists can reconstruct the structural arrangement of atoms within the material. Today, synchrotron radiation is widely used for scientific research in diverse fields. A number of groundbreaking discoveries were rendered possible only with the advent of synchrotron radiation. Several Nobel Prizes have been awarded in the area of synchrotron science and technology. Recently, the structure and interactions of proteins linked to COVID-19 have been solved using synchrotron radiation. Truly, the use of synchrotron radiation as a light source has revolutionized modern scientific research.
Okay, so I hope this was audio was there. Hello, hello.
Yes, sir.
Hello.
Audible is. Yes, sir. Yes, sir. Yes, sir. Audible.
Okay. Okay. So this is the now view graph of the Indus facility, as you already saw in this video clip. And now I go to the next slide where I have some tabulated the various beam lines set up at Indus 2. And right now, 17 beam lines are operational on Indus 2, and which has a different type of experimental techniques like scattering, spectroscopy, then imaging, and this BL1, for example, is a soft X-ray based spectroscopy, which is in the range of 100 to 1200 eV. So can be used for UV soft X-ray absorption spectroscopy, which is complementary to what I'm going to show today, a hard X-ray absorption spectroscopy. Then we have also a beamline for engineering applications, so it can handle the odd objects for engineering applications for XRD imaging, XRD characterization. Then we have a beamline for reflectivity in the soft X-ray region, and this is the beamline for X-ray imaging BL4, which is in the energy range of 8 to 35. And we have also beamline the BL7, that is for micromachining, X-ray lithographic kind of study, and this BL8, and which is dedicated that more will hear in our.
Sir, your audio is not disturbed. Sir, your audio is not clear. Sir. Yes, sir. Sir. Yes, sir, your audio is not clear. Sir. Yes, sir. Sir, your audio is not clear. Yes, sir. Please plug in and plug off and plug in, please. Sir, it's not audible. Sir. Yes, sir. Yes, sir. It's not audible.
Audible now?
Ah, yes, sir. Yes, sir.
So how long it was not audible?
Yes, sir. Yes, sir. Clearly audible.
Okay. So you could see this the last slide only, or much before that?
Yes,
It was
sir.
not
Yes,
audible.
that last slide, that yellow plus slide.
That beamline listing, that was
Yeah,
audible.
yeah. Yes.
Okay, I'll just again share the screen. 1 minute. Sorry. Yeah, now screen is visible screen.
Yes, sir. Yes.
Okay.
Just
So
previous slide.
this
Come
slide
from the previous one.
this slide was okay.
Ah, yes, sir. You want to start from this?
Yeah. So as I mentioned, there are 17 beam lines which are operational and which covers scattering, imaging, spectroscopy techniques, and as well as the angle resolve, which includes the band structure in solid state, including imaging and for engineering application. So which is listed here, and the beamline most recently has been added up is the angle resolved photoelectron spectroscopy, as well as the small and wide angle X-ray scattering beamline and engineering application beamline. So for more details, we can visit the website of Rajaramana Center for Advanced Technology. So you know more details and application. Here I have just given the glimpse of what can be done with the beamlines here. And this is the listing of the beamlines at Indus 1, which is a UV source, and all the beamlines are here dedicated for the spectroscopic studies. And you can see this high resolution vacuum ultraviolet beamline, as well as the third one, photovisible beamline. These two are mainly for atomic and molecular spectroscopy. And then we have a angle resolved photoelectroscopy beamline, which is the energy range in UV. And what you saw the recent edition in Indus 2, that goes up to 1000 eV, but whereas this goes up to 200 eV. And then we have an infrared spectroscopy beamline, which can be used for high pressure microscopic studies at low temperature. And then we have also got this photo absorption spectroscopy studies beamline for local studies, but in the UV region. And we have another PS beamline for density of states, and then reflective beamline. Okay. So now I'm coming to the next topic, that is the introduction to EXAFS. I'll start, and then its history and other aspects of this technique. So this is the common spectra. You must have been familiar that this is the absorption coefficient versus the photon energy plotted in this graph, and the whole spectrum is known as, in general, X-ray absorption fine structure. But further, it has been divided in two components, and which we'll see more in the next slides. It is called extended as well as X-ray absorption near structure, that is GENS. So basically a spectroscopic technique, but normally the spectroscopic technique is used to find the energy levels. Here, using this technique, we try to find out the structure at the local level in any material. So just a brief history of EXAFS. So although it was discovered long back, more than 50, 60 years before it became popular, as the old technique in 1920, that it was known as GENS, and also it was called as coastal structure. And 1930, this EXAFS modulation of electron wave was given by Kronig, and he called it a long range order. And that time 2 papers were published on this. But in 1934, EXAFS observed in molecules, and then Kronig proposed the short range theory, but did not include the de Broglie factor or mean free path. So that was not complete, and so EXAFS was known as a Kronig structure by that time. But Kronig never appreciated this short range order for molecule, so he was it was not giving full picture. So there was this confusion was there till 40 years. When 1970, in the 1970, EXAFS was rediscovered by this group of people like Sayers, who was a PhD student in the University of Wisconsin with Stern and Lytle, and he was an experimentalist, and Lytle was a theorist. And he demonstrated that the Fourier transform of this EXAFS oscillations gives a pattern which is close to the radial atomic density distribution. And then further, this was boost was there due to availability of synchrotron source during that period. And this is the first paper of this Stern Lytle together, who gave this paper, published this paper on.
Sir, slideshow, please.
Now this slideshow?
Yes, sir. Yes, sir.
So just a minute. So this was the paper which revolutionized the EXAFS technique, and by where the title says it is a new technique for investigating non-crystalline structures, Fourier analysis of the extended X-ray absorption fine structure. And so with this modern theory, it was ideally suited to map the local structure, which is sensitive to local distortions in the structure, and which results from the interference of outgoing and backscattered photoelectron waves, and the range of photoelectron is limited due to core hole lifetime and the inelastic. So this was the main outcome of this paper, and later on with the synchrotron and this theory available, this become a common technique for researchers across the different diverse areas of field. So here we just come to some more basic here, and you can see here this is a plot of the cross section of X-ray in a material in the energy range of 1 to 100 keV, and we can see here the predominant part in this is the photoelectric absorption is the top curve, and the Thomson and Compton is much less in this region. And you can see there are different, apart from this monotonic decrease in the cross section, there are two conspicuous this rise in the absorption cross section, and these are known as absorption edges of the due to the particular element, and that's why this becomes a very element specific this technique. So if you zoom out of this region, let us say this is germanium K, and then you see in detail. So these are the wiggles, which is called the EXAFS, which is beyond 50 eV of the absorption edge, and area near the absorption edge is called gens. I'll explain about gens later. And so basically this is due to the photoelectron wave which is coming out. So if you can understand like this, like when you sign the photon energy, electron is knocked out, let us say from K cell, so 1s, and this photoelectron wave which comes out, if it sees some backscatter, and that is possible only in the condensed metal. So this is sensitive to only condensed metal material. So then there is a interference, quantum mechanical interference between the outgoing wave, this is a white line, and then the dotted structure, which is a backscattered wave, and this interference gives rise to this kind of oscillations, and therefore this is sensitive to the neighboring atoms, or the number of atoms, or the type of atoms, and so on. Okay, so what is the origin finally of the this fine structure? So basically it can be understood by using this dipole matrix element, which is proportional to this final state wave function, Hamiltonian and initial state. And so therefore, what is the initial state? Is the state where this X-ray knocks out the electron, and then it comes out in the continuum, and this photoelectron gets modified due to the surrounding. And therefore, this dipole matrix element gets oscillations, oscillatory behavior because of the change in the outgoing wave. So the amplitude of the backscattered photoelectron at the absorbing atom will vary with the energy, causing the oscillations in the mu e, and that are called EXAFS. So basically, this is the for electron X-ray wave, which is shining on the material, and this is the wave coming out. So if there is no backscatter, then you see just outgoing wave propagating, and it will decay, but it will not give any oscillations. The moment you have a scatterer, then you place. So this this picture, in this picture, you see there is no oscillations here because there is no backscattered wave in the neighbor. But the moment you put a neighboring atom, so this is scattering atom. So then this is the outgoing wave. Let us the blue one, and the red one is the backscattered wave, and then you see the interference pattern, and so this interference pattern gives rise to the oscillations over this monotonic decreasing mu as a function of energy. And this absorption, the edge position, that is the absorption edge, gives rise to characteristic fingerprinting of the particular element present in the matrix. So that's why the EXAFS is element specific technique, and which provides element specific structural information about a sample by the analysis of its X-ray absorption spectrum. And also it allows determination of chemical environment of a single element in terms of neighbors, interatomic distances, and spectral disorders. But why we say that it is a short range order, that you can understand by this universal curve, which is a mean free path versus the electron kinetic energy. So you can see there is a around 1000 eV, and so the mean free path is less than 10 nanometer. So, and that's why when the photoelectron, which is coming out of the system after the threshold energy E0, it can vary from the zero kinetic energy up to 1000 eV, and beyond that it decays due to the core lifetime, and so therefore it is sensitive to only short range order, and therefore it doesn't require long range order, and even low concentration can be detected. So there are some terms and conditions in EXAFS used in for analysis of the structural parameter. So this is the raw data which is obtained from the transmission absorption curve, and this is the mu e, which is derived by this Beer-Lambert's law, and then you see this is the oscillations. But mind you, this oscillation, although it should look like sine wave, but it is not really sine wave, although you see the sine term here. But the thing is that it is the mixture, or you can see it is amalgamation of many sine waves of different frequencies and different amplitude. So it is a convolution of various sine waves, and which is produced due to different scatterer at different distances. So we'll see more how this sine wave is then filtered for each frequency. And the extraction of this information is possible because of the jet dependence and because of the photon energy dependence of the phase shift of the central atom, as well as the amplitude and phase shift dependence of the backscattering atom. So you can see central atom is this jet dependence. For example, carbon, germanium, platinum, it has a totally different phase shift behavior as a function of K. K means finally it is photon energy. So this is the since kind photoelectron wave we are talking of. So this is a de Broglie wave. Similarly, there is a diversity in the phase shift and amplitude of the backscattering atom, which gives us the opportunity to give a contrast in the signal due to different scattering atom. And so from this mu, we get the EXAFS function, that is for example chi e, by using this equation, and mu e is this plot, and whereas the mu 0 e is the monotonic decreasing mu e, which is as if there is no backscatter, then how it will behave. So that is considered as a atomic background, and this the difference between these two pre-edge and the post-edge called delta mu0, which is used for normalization. And by using this chi, we get then conversion by using this formula, that is de Broglie wave is equal to E minus E0 by h cross square under square root, and we get the final EXAFS equation, which is derived based on the equation the dipole matrix element and other factors like core hole lifetime, phase shift, other scattering factor, etc. So you can see in this there are various terms like n, which is the number of coordination number of neighboring atom. Then we have S0 square, which is a geometric constant for the experimental geometry. Then scattering factor F. Then this is the Debye-Euler factor, this one, and this is the decay parameter, and this is of course the sine 2kr plus delta, which is function of the bond length as well as the phase shift due to back scattering atom. Okay, so with this equation, we can understand these are the parameters which can be determined from the analysis of this EXAFS equation. So further to give you feeling that how the interference distance is related to the sine wave frequency. So for example, if R is more greater, then you will see more high frequency signal compared to lower R. And similarly, amplitude, how with the changing amplitude, how it is proportional to coordination number. So you can see with the coordination number 2 and coordination number 4, how the sine wave frequency changes. Similarly, with the Debye-Euler factor, what is the behavior? If you see Debye-Euler factor is, if it is increased from 0.005 to 0.001, so it decays faster. So beyond 10, it decays. So this just to highlight that how the different structural parameter gives rise to changes in the EXAFS signal. Now, how to get EXAFS data from exhaustion spectra? So just quickly, I'll show. This is the mu raw data. From there, we do the background subtraction process, and finally from there we get the chi k, that is the EXAFS function, and then by Fourier transforming we get a radial distribution function. And in this, for example, you can see the first peak denotes. So just by seeing qualitatively, you can say this is the first iron oxide, then next iron, and this is the next iron manganese. This is a sample manganese doped iron oxide. So what is the accuracy we get? That is, I have just listed here. So for example, distance we can obtain up to 0.01 accuracy between the observer scatter distance, and we can get coordination number and Debye-Euler factor with plus minus 20-25%. And it is scattering atom sensitivity is that is plus minus 1 for up to Z is equal to 6 to 17, but below Z6 we I mean Z is equal to 20 to 35, we get Z plus minus 3 sensitivity. So elements that are next to each other in the periodic table have barely distinguishable photoelectron scattering characteristics. That's why it cannot be distinguished by EXAFS. So now coming to experimental methods. So once we know the mechanism, how it is, what is the reason, and now I come to what are the experimental methods one should apply while planning experiment. So there are two methods. So first one is the transmission detection. It is the most conventional method where the sample is placed 90 degree to incident beam, and the transmission intensity is recorded by a suitable detector. But there is a caution that for sample preparation, otherwise you will get artifacts in the recorded spectra, that one must have a homogeneous sample thickness and also a homogeneous grain size, and it should not be, the grain size should not be bigger than a absorption length. It should be free from pinhole, and it should have also very optimum thickness. Normally age step of 1 is advised for getting the good spectra, but this mode is suitable only for concentrated samples. As you can see, for example, here, this is the two cases. One case, the metal is present in 1%, and this is very suitable for transmission. The moment we go down to 50 ppm, we see hardly any features. So in that case, you have to go for fluorescence. In also another case, although the percentage is here 1%, as in the previous case, the moment you change the this background absorption, that means the matrix. Here, matrix is a bromine, which is high Z. So then also, although concentration is as same as the earlier case, then also we see the very little signal. So in these two cases, in such cases, we go for a fluorescence mode of detection. So it is best suited for dilute samples as well as for thin film deposited sample, and which is given by mu is equal to the fluorescence signal divided by incident beam signal. There is another mode that is called total electron yield, which is normally applied in the soft X-ray regime, where the fluorescence yield is very poor. So then we use the total electron yield. Okay, now I come to give some more details about the GENS. So GENS, the know it is X-ray absorption near spectroscopy. So as name suggests, it is the structure or the features near the absorption edge. So this is the edge, and this region, it has three regions. You can say the pre-edge, which is just before the edge, then edge, which is sensitive to the chemical states, and the beyond edge up to 50 eV, which is called near edge structure, which is sensitive to symmetry, and also the density of states, of unoccupied density of states, and the angle and other information. So for example, this is the titanium case in TiO2. And you can see just by seeing this pre-edge features, we can tell about the symmetry, whether it is a rutile or anatase phase. And by looking at the position of the state oxidation, looking at the position of the absorption edge, we can tell about the chemical state of the element present in the sample. So this is an example to find out the oxidation state from the GENS analysis. So the main absorption edges of many elements. So significant binding energy shift with the oxidation state, which is also known as chemical shift. And you can see this is a plot of manganese K absorption edge versus the manganese valency. So you can see as the edge energy position is shifted to higher energy, the valency is shifted to higher valence state. So for example, this 5 valence state is the highest 655, which is again shown here in the graph. This is the manganese foil, which is a 0 state, and then as you go on up to manganese 5 plus, so gradually there is shift in this absorption edge up to 655 eV. So this can be used as a fingerprint for the getting the idea of the oxidation state, and also by fitting this linear combination fitting, we can also get the composition of different valence state in the material. This is the example of how we can just say about the local coordination environment. So for example, here is a case of barium titanate, and we have two cases in the where the titanium is in 4+ state. The chemical state is same, but the nature of environment in one case is tetrahedral and in other case is octahedral. So in the case of this blue curve, where it is the tetrahedral, is a strong pH peak, which is due to 1s to 3d transition. Although 1s3d is dipole forbidden, but then it gives a hint that there is a hybridization between oxygen 2p and 3d. So more the hybridization, there will be enhancement in the intensity, and therefore we can say very confidently that this compound has the tetrahedral coordination sphere, whereas in the case of octahedral case, the 1s3d transition is forbidden, is a quadruple transition, and therefore the intensity is quite weak in this case, and that's why it is a symmetric, highly symmetric case. So there is a less distortion in the geometry, and therefore you can say it is a octahedral. So this is an example to show how local environment can be fingerprinted by seeing the GENS spectra. This is the information again on the chemical state information. Is example on copper. So you can see from copper or metal 0 state to various state, we can see there is a shift in the absorption edge, and which gives the higher transition energy, and which gives again the idea of the oxidation state in the material. So this is about a slide that's showing the GENS interpretation. So it can be described qualitatively and nearly quantitatively in terms of coordination chemistry. What is a regular octahedral or distorted octahedral, or is a tetrahedral, Then also it can give molecular orbital band structure picture with the multiple scattering. Also it tells about PD orbital hybridization, as we saw in the barium titanate case. It tells about the density of available unoccupied electron states, and also about multiple scattering, which finally gives rise to information of the bond angle also. So Jane's calculations are now feasible by this FAF8 and above software, which is available in the net. And beyond FAF8, we have to purchase at a nominal cost. But with this tool and the experimental result, one can get the bond angle information as well as the band structure information. So this is a summary of information from Jane's. So pre-H gives the local coordination environment around the absorbing atom, dependence on the oxidation state, whereas the H gives the dependence on the oxidation state, chemical shift, and the Jane's part, that is the beyond the H to 50 eV, it gives the atomic positions of the neighbors, interatomic distances, and bond angles. So now I come into EXAFS beamlines at Indus 2. So these are the two beamlines, the energy dispersive. First, it was developed in 2008 with the objective to have a application which can do simultaneous record the simultaneous EXAFS spectra in a single shot, which with the application of capturing the kinetic studies. And then later on, high resolution energy scanning EXAFS beamline was developed for a fluorescence mode of detection for dilute samples. So this is the photograph of the first beamline, and which is dispersive EXAFS which is housed in the shielded hatch, and this is the optical geometry. So it has a combination of pre-mirror and the bendable polychromator, which gives rise to focus beam at the sample position, and when it diverges from this focal point, it gives rise to the spectra is recorded by position sensitive detector. So simultaneously, single shot whole EXAFS spectra is recorded, and so it can be used for a kinetic studies kind of study. This is the experimental station of the dispersive beamline, and this is the second beamline. This is scanning EXAFS beamline. So you can see the core of the beamline is a double crystal monochromator, silicon 111 based double crystal monochromator, and this is the view of experimental station, and it has several auxiliary facilities like CCR, helium cryostat, and high temperature cell, and various detectors for transmission and fluorescence measurement. And this is just schematics of the, so whole beamline from the source to the station is 37 meter long, and which is maintained at ultra high vacuum throughout the beamline. And you can see the two mirrors. The mirror one is rhodium, and the second one is also rhodium coated, and in between then we have a double crystal monochromator. So what are the elements you can probe with this existing facility? So we can use this beamline in the energy range of 5 to 30 keV. So we can probe basically titanium to antimony for K edges and lanthanum to uranium for L edges. And these are the, over the years, various facilities have been set up at this beamline. For example, from as low as 10K to 1000K temperature dependent studies can be done. And recently we have set up a 2 Tesla magnet for Excise in the magnetic field at room temperature. Then we have recently augmented with a detector with a 4 element, which can be used for metalloprotein or drug sample. Then measurement is also possible on thin films for precise mounting of samples and control for angle dependent studies. Then we have set up for facility for in situ studies, which reaction cell with a UV visible probe. Then facility for battery charging discharging studies to correlate the performance with the structure. Then we have a facility for heterogeneous catalysis with a gas chromatograph for simultaneous measurement of reaction products. So these are some of the view graph of the facilities here, and this is the setup view graph for the in situ XS measurement setup. For this is in situ XS measurement for lithium ion batteries. Then setup for catalysis and photocatalysis reactions. The more details we can see in this reference paper. So finally, with these beamlines facilities, what are the applications we can tackle? So basically, using the EXAFS technique and the available facilities, one can go for local structure in a non-crystalline matter, either in a solution or thin film, local environment in of an atomic impurity in a matrix of different atomic species, then study of systems whose local properties differ from average properties, then detection of very small distortions of local structures is possible. So I'll come for the last part of the examples. So these are the type of materials which have been handled with this facility, starting from nuclear materials for waste management application to luminescence materials to various industrial application, and including electrochemical reaction studies, catalytic systems, sensor materials, in situ studies, also Ayurvedic drugs, etc., has been used this beamline we use for such studies. Now I have picked up some example studies from these various studies carried out using these beamlines. So this is the example on cationic disorder studies. This is a pathway for demonstrating inverse exchange bias in this gallium GD to RuO6. So which is a double perovskite samples, and it was studied by EXAFS. And the EXAFS indicate that a strong anti-site disorder between cobalt and Ru. And there are two sets of samples. A slow cooled sample shows uniform disorder, whereas the cooled one shows the islands of disorder. And James measurements confirm that there is a mixed valence for both Ru and Co. And the difference in disorder in the two samples nicely account for the differences in the magnetic properties. So these various models has been suggested based by simulating the various scattering path starting from RuO to Ru, so that the best fitted curve is plotted here. And using this analysis, this is the conclusion for confirming the strong anti-site disorder in the sample. And this is published in PRV recently. And this is another example where doping effects on the local structure of nickel oxide core cell structure has been studied, and the coordination of all the atoms are found to vary on doping, and measurements indicates that cobalt doping and geo incorporation suppresses the antiferromagnetic charge ordering and lead to spin flop meta magnetic behavior between these temperature range. And this is done with the in collaboration with our one user, Dr. UP Gabai, and this has been published in PCCP. Now, this is another unique example where the synchrotron properties, that is the polarization properties of synchrotron, has been used to demonstrate the effect of germanium on autodiffusion, effect of germanium autodiffusion on the bond lengths of gallium and phosphorus atoms in this thin film, that is gallium phosphide on germanium. And you can see there are two geometries. In one geometry, as you know, this synchrotron light is linearly polarized in the plane of the electron orbit. So we have chosen geometry so that in one case the electric vector is parallel, and in one case is perpendicular to the sample surface. And by these studies, that is called in plane and out of plane EXAFS study, we have shown that there is a asymmetric variation for the in plane and out of plane direction of this thin film, and therefore this is locally, this is a local variation which is not visible in the XRD pattern clearly. But although XRD showed that there is a tensile strain, but then the structure was there is no clue for structure. So EXAFS become helpful by locally probing around the germanium. So this is another example on polarization dependent study, and here the objective was to confirm whether the zinc oxide in this material, that this is the 2D structure of the sample. In this sample, whether the zinc oxide is a graphitic zinc oxide or it is a normal zinc oxide like any bulk zinc oxide. So this, with the help of DFT calculation and other complementary technique, we could say very confidently that the zinc oxide between these two reduced graphic oxide is a predominantly a two-dimensional zinc oxide. So it is called graphitic zinc oxide. So this was done with a combination of GENS as well as EXAFS, and you can see clearly there is a difference between the zinc oxide of the bulk and compared to this this one, I mean 2D sample. And the same thing was also observed in the GENS studies. You can see in the blue, which is the perpendicular, when the E is perpendicular to the C axis, you see the doublet, where in the other case you see the single peak. Now this is another example of in situ studies of the, hello, how much time I have?
5 to 10 minutes.
Okay. So this is it gives insight into charging discharging of magnetic electrode based lithium-ion battery. So this was done in situ with the setup which has been developed at RRCAT Indore, and this is the different EXAFS spectra as a function of voltage applied, and from this studies we have got this pathway of the reactions. So it starts from Fe3O4 to, then it is intercalation reaction, then conversion reactions at it gives to FeO, and subsequent cycles it gets to metallic iron. See, the detail are given in this recently published paper in the PCCP. So next, I'll just skip this. This is the time. So this is another example of EXAFS for thin film, and this EXAFS can be in the surface sensitive mode. It can be used to verify or to analyze the interface thickness as well as interface roughness in the multi-layered thin film by a technique called X-ray standing wave technique, using this setup for gauging resistance X-ray at beamline. So this example studies on nickel titanium multi-layer, which is for used in neutron mirror application, and so I not go in detail because of time now. So, but you can see this is a model we have generated from this EXAFS analysis, that how this whether, because this is very important parameter to explain why neutron reflectivity is going bad in these two conditions. Either argon plus dry air gives much better, or in the pure argon. This is another example of Ayurvedic drug where the objective was to seek evidence towards its non-toxicity. Normally, we are afraid of this mercury drugs, thinking that it is a poisonous. But we have confirmed that from the study that the Rasasindura, this Ayurvedic drug, is non-toxic, and it is a very sturdy nanomaterial with a 24 nanometer average particle size. And the whole Rasasindura has a same structure as non-toxic alpha HGS. And this has been done with the combination of GENS, which is plotted here, and this is the EXAFS. And you can see this is the Hg0, that is the pre-age, and this is the C. So A and C is not present in the Rasasindura, which is the blue one. And from here also you can see there is no metallic nature of the bond present in the EXAFS spectra. So this is an example of EXAFS where we have found out the confirmed the purity of the phase, like whether it is which hematite, magnetite, or the goethite, which phase is present in this iron oxide nanoparticles by looking at the EXAFS oscillation and fitting different models of hematite, magnetite, and goethite, and whichever gives the best fitting result. Like this is the R factor, which is a measure of the fitness of the experimental spectra. So this gives a very fingerprinting of the for the unambiguous determination of the structure of iron oxide nanoparticle. Okay, so this is the example on in situ studies on the growth of novel biometallic nanoparticles in situ X-ray study, and you can see this a plot the time versus the exact spectra, and can see from 0 second to almost 500 second, the spectra are plotted, and this is the from this curve, this is the exact spectra generated radial distribution function, and you can see at 0 second there is a AuCl bond formation. As you proceed with the time, you can see this bond features is disappearing, and another bond feature is appearing, and you can see AU and AUPT bond started appearing, and slowly this bond, AuCl bond, is vanishing. So very clearly in situ you can see the bond breaking of PTCl bond breaking and PTPT or AU bond formation. And same thing is shown here, the coordination number variation with the time, and you can see this is the PTCl bond, the coordination number is decreasing with the time, and in this curve you can see the AuCl bond is breaking, I mean coordination number is decreasing, whereas the AU bond is formation is increasing. So very beautifully this EXAFS can help to elucidate the understand the reaction mechanism. This is another example of operando X-ray absorption spectroscopy for studying the heterogeneous catalysis with a cobalt catalyst CO3O4 nanoparticle. So this which is used for production of the fuel from syngas, and the objective here was to investigate the deactivation problem. So from this analysis, EXAFS analysis, in situ EXAFS spectra analysis, we have all found that this signal at 400 degrees, sorry, 1 minute. See, the activity they monitored at different temperatures were used to study the deactivation process, and from this study we have concluded there is no oxide formation in this study which leads to this deactivation. Basically it is a some carbon deposition is the cause of structural deactivation. So with this I come to the last example, and then I have come to the summary, and where in this I have just shown the unique properties of synchrotron source as a tool to probe any material. And by this advent of synchrotron source, the EXAFS has become a popular technique as a unique tool to probe element-specific local structure in any material, whether it is a non-crystalline, nanomaterial, or solution phase. And it can lead to various applications to local environment of an atomic impurity in a material, non-crystalline or solution phase, and the study of systems whose local properties differ from the average properties, and detection of very small distortions of local structure. And the versatile EXAFS facilities and Indus can be used for materials science study in the area of nanomaterial, functional material, catalytic studies, battery electrode material, in situ operando studies, drug application, and so on. So with this, I come to the end of my talk, and all this is a mega facility. It is not possible without the contributions of all my colleagues and past our bosses like Dr. N.K. Sahu and Siddhas, and all other users of BL8, BL9. Because of their feedback, we could set up the new facilities, which is useful for as a national facility for all of the users. And I must acknowledge the Director Physics Group for facilitating the grant, and Director RRCAT and Dr. Bach for giving grant for building up these beamlines. And this is just to slide to show that how to use the beamline facility. You can visit this website and you can register yourself and then write down the proposal, and you can then use any beamline. So this is the Indus 1 beamlines available, and these Indus 2 beamlines. And these are some resources which I have used and can be used for further detailed studies. And these are resources on Synchrotron handbook, and these are resources on EXAFS, and these are various tutorials. So this, I thank you all for patient hearing, and I welcome you all for any comments, questions. I'll be happy to answer. So anyway, thank you.
Thank you, Dr.
Audience. When we required to approach the EXAFS instead of XPS. So as you said that the Indus having the XPS, EXAFS,
Yeah.
SCAX, right?
Yeah.
So when we have to approach that one, whether any resolution based analysis or some other thing.
No, whether what can you repeat that last part?
So we are having one material.
Okay.
So how to choose that EXAFS will be better result than the XPS?
No, so we have to apply judiciously in the sense,
I
XPS
know about
normal.
that things. Yes, sir. I know about that. But for the audience point of view, I am asking you.
No, so the one thing is there, if you want to study the bulk that so then your gens will give complementary information to XPS. And also many times, for example, in nanomaterial, we see that surface property is different than the bulk. For example, let us say, one example I'll show you, like cerium phosphate nanoparticles. When I choose XPS, it gives cerium 4 plus, okay? But the properties, physical properties is contrary to that. I mean, like luminescence properties. So then we apply the gens, and gens we found it is predominantly only cerium 3 plus. So based on the our physical properties, then we decided to choose the gens also to complement the result. So that is one part. Plus, if you also the kind of density of states what you get from XPS is from occupied states, whereas in gens we get the density of unoccupied states. So that is the two contrasts. So depending upon the what objective you have, you can choose. Am I clear to answer or? Hello?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. So you are saying that cerium is a issue, right? So the cerium, terbium having the various oxidation state. So what I am asking, after the settlement of the oxidation, I am going to come with my material only, right? So during that instrument and analysis also, there may be a possible to shifting of the oxidation states, right, sir?
Okay.
Am I right?
Yeah,
So
maybe.
you are saying it will be a little bit challenging one to identify the concerned oxidation state.
No, if it is, you mean if your material is photosensitive, I mean, it is some radiation damage kind of thing, then it is a challenge. But if it is not sensitive to radiation damage, then you will get the real properties. Like in one case, you get bulk, like micron level sensitivity in gens, for example, and in XPS we get like 80 nanometer, 80 in that level sensitivity.
Okay.
So that is the difference.
Thanks, sir.
Yeah.
So any questions from audience or
Yeah.
participants?
Yeah, I have. Thank you, sir. It's a very good talk because rural people don't know these very advanced techniques. EXAFS, where is it and how to use these EXAFS instrumentations in our India, because this is very limited centers in India and Indore and Mumbai. So this is very good platform for our students as well as our research scholars in south part of India, particularly south part of India. Okay. So I come to my question. This is not question. Just I like to discuss my research with you because I'm doing single atom and single side photocatalytic materials. So I had some experience in visit Beamline in Beijing, Chinese Academy of Sciences in Beijing, because I did postdoc in Italian Institute of Chemical Sciences, Chinese Academy of Sciences. So I had good experience and good interaction with some scientists. So I prepared some materials using doped with some metal oxides. So I prepared some materials like iron on metal oxide, but my iron atomic percentage is very limited. like 0.02 or 0.404, like that, because I predict from Moss Bayer spectrum, because I worked on Moss Bayer data center in Italian Institute of Chemical Science. So I got some spectrum, some Moss Bayer, and I predict this is a single side, but I cannot confirm from Moss Bayer spectrum. So my professors told you need to take EXAFS or XENES spectrum.
Yeah.
Can yeah. Can you say some some ideas about this? Yeah,
No,
please.
definitely you can do Janes and exams, and from there you can complement your result. Single atom, this kind of catalyst people are already using in our beamline here. Some users from IIT Guwahati and I think IIT Delhi people are using. So
Oh,
we can definitely, you can approach us. You can write the proposal, as I told you, that website. You can
okay.
register and write the proposal, and then we'll allot the beam time, and you can definitely use. And now the COVID is relaxed, so now we have started users to visit our facility so that they can have a first-hand experience. Especially your PhD students, they will get exposure by using this facility. And
Okay. I need to know how much limited atomic percentage is needed to take HCl,
so,
because
for
it's
example,
in, yeah, yeah.
it depends on the matrix. I told you the example: 1% in a low Z matrix and 1% in high Z matrix. So, but we have a detector, single element detector for fluorescence detection, and that we have seen percentage level. We can easily get the Gen spectra. If it is in low Z material, then maybe you can go down in ppm level also. So maybe we have to just try once. We can, maybe you can send one sample for a test example. I will just have a run. And but I feel similar thing has been done past, so it should be possible to do.
Okay, sir.
There is no
Okay,
harm
thank you.
because you don't have to apply for any visa or anything. You can just post me the test sample. I will
Okay,
try.
okay,
If
okay,
it is feasible, then you can further do that.
okay, okay. Thank you so much, sir.
And
Any other query from participants?
और डॉक्टर ने सब दवाई वगैरह भी बंद कर दी है, तो ईश्वर की कृपा से जल्दी हो गई सब इनकी रिकवरी और ठीक हो गए हैं। तो जब ये बीमार पड़े थे ना तो
Please conclude, please. Sir. Yeah, please. Please conclude this.
तो आप लोग सामान
No.
के लिए ही थे ना।
So I think no
Sir?
queries. I
Yes.
think no queries are there from the participants. So we are very thankful from my side and from the organizers. Dr. Jha, you presented a very informative and very interesting talk. So thanks from our side. Thank you.
so I
Sir,
also I also want to thank the organizer for this novel cause which we have started, and I offer myself as a volunteer, and especially from the next year I will superannuate from this job. So I'll be very happy to volunteer myself for this trust.
welcome, sir. Welcome, sir.
And my objective will be, after my superannuation, to propagate this unique science with synchrotron all over the country, especially the universities which are underprivileged. For them, I want to make aware this source and as well as various techniques, not only EXAFS, all the other techniques, hard X-ray PES, other techniques, X-ray fluorescence. That also is very important for environmental science application. And I came to know that many universities are having environmental science department, and one can send their students for PhD, you based on especially on synchrotron, so they can spend time and do their PhD, part of the PhD here. So that is my objective, and I think this I am very fortunate to have this platform. I got introduced to this platform, and I'll be happy to contribute through this platform to propagate the science using synchrotrons. So I have expertise in that area, so you can use me, and especially more. I am freely available after March 23, 2023. Okay, so this is the offer from my
Yes,
side. Thank you, and
yes, sir.
thank you
Yes,
once
sir.
again. Okay.
A very warm welcome for your interaction with us. When I am in the RRCAT, your interaction with me, and that's the initiation part of this case. So I know about you a little bit. You are you are a social free people. You are a social free helper to others, those who are from the scientific approach. So based on that interest, I am approaching you. You give the opportunity with us. Definitely, we will be a good platform which you connected with us. Okay. If you want to promote that EXAFS or Indus Center, RRCAT, whatever it is, you
Yeah.
know about your well known about the synchrotron person. So we are the perfect 100% perfect fellows to enrich that knowledge towards the audience, that is the scientific community. Okay. Definitely, we will plan in the future projects also, sir.
Yeah, definitely.
Thank
I
you
am
very
there.
much.
It is must we should do this, propagate this part, this technique, because it is still underutilized, not fully utilized. So, and
Yes, yes,
there is no cost for a beam time, as you know, and
yes, sir.
also
Yes.
two students can get their train fare also to come to this facility to use the facility. So that also is there information. I'm just telling you. Okay. Thank you.
Definitely. Oh,
Thank you.
thank you, Ravi, sir. Thank you. What I enjoyed with you, now I am trying to convey to the next peoples. That's, as like that, you are also saying, I am ready to promote such a thing, whatever I am having the science, right, sir?
Yeah.
Very helpful, very helpful. Definitely, we will connect with some other projects, sir. Okay,
Yeah, sure. Okay. Thank you.
okay, sir. Thank you.
Okay,
Okay.
thank you. Namaskar.
Namaskar, sir.